So because I'm asking you guys to take a look at some supplementary videos on the topic of trigonometric substitutions, I'm not going to do a really super long lecture myself again. I already gave you one kind of lengthy lecture with a bunch of examples, but this is a difficult topic, so I want you to spend a lot of time looking at it, but I also want you to look at it from different people's perspectives. And so what I'm going to do here is, this is just a very short lecture on a summary of what we concluded about working with trigonometric substitutions. And so I want to just kind of summarize the rules that we have without really going over anything in particular, but just kind of saying, here are the patterns that you're going to look for. Here's what you're going to do when you see those patterns. And the key things that you want to remember, right, are the Pythagorean identities. So we have sine squared theta plus cosine squared theta is equal to 1. That is one of them. If I divide both sides of this by cosine squared, of course, I get tangent squared theta plus 1 is equal to secant squared theta. And then I can also take this second form of the identity and I can rewrite it as secant squared theta minus 1 equals tangent squared theta. So ultimately, what we're kind of looking for is, when can we get something into a form where one of these would be helpful? Well, this form is going to help if I have something that looks like ax squared plus b squared. Or actually, let's write it as a squared x squared plus b squared. Although usually, actually, let me take that back. Usually what we want to do is we want to take this one and write it as 1 minus sine squared theta equals cosine squared theta, or something like this. And then in this case, what we want to look at, because the one that I just wrote down is actually what we want for the next one. So the second case is going to be when I have something that looks like a squared x squared plus b squared. In this first case, then what we're going to want to look at is, and let me erase this so that I can write everything next to each other. So this is going to tell me that 1 minus sine squared theta is equal to cosine squared theta. So we're going to use that form of the Pythagorean identity. And in this case, what we need to have is something that looks like a squared minus b squared x squared. And in the third case, we're going to want to look for something that looks like a squared x squared minus b squared. But it's never going to be quite like, to get it into this form, then what you need to do is you need to rewrite each of these things in the following way. So what I can do, and let me write this a little bit further over. I did not think this out so well, did I? A squared minus b squared x squared. I can rewrite this as b squared times a squared over b squared minus x squared. And then for this next one, I can rewrite, you know what, let's just write it underneath because I don't really have horizontal space here. Again, factor out a b squared. So this becomes b squared times a squared over b squared x squared plus 1. And then what we can do for this last one is we can rewrite this as b squared times a squared over b squared x squared minus 1. And there we go. Now, the reasons why this is going to help us is because now, in this first case, in fact, for this first one, let's actually rewrite this in another way yet. And let's rewrite this because I want to have a 1 in here. So let's actually factor out an a squared. We would get a squared times 1 minus b squared over a squared x squared. There we go. That'll be a little more useful. So now we have this into forms where all of these are useful. Because in this first case, in order to get what I want is for this piece to become a sine squared theta. So this here is going to become sine squared theta. In this case, I want this a squared over b squared x squared to become a tangent squared theta. And in the third case, I want a squared over b squared x squared to be a secant squared theta. And I can just set those things equal to each other and go from there. So what I do in each of these cases is, if you have something that looks like a squared minus b squared x squared, factor out the a squared and then do a substitution of b over a times x equals sine theta. That will give you b squared over a squared x squared is equal to sine squared theta and allow you to simplify this. In this second case, what we want to do is we want to replace that with a tangent. So we would have a over b times x equals tangent theta. And in the third case, we want to replace a over b times x with secant theta. So there are three cases here that we want to deal with. And in each of these cases, there is a set way to go about figuring out which thing to do. However, while it's a good idea to memorize this table, which is given to you in your book in a much, much cleaner format than me writing it on the board here, but while it's a good idea to kind of memorize the table, I'm not saying you shouldn't. Personally, I feel like it is more useful to understand where it comes from. Because if I just try to memorize each of these formulas, I will end up forgetting and messing them up sometimes if I do them. But if I think about, okay, what is the identity that I want to use? Well, if I have something where I want to use a particular identity, I can recognize the form of that identity and then go from there. So for example, instead of just memorizing the table, let's suppose that I want, like, the expression that I see is something like maybe 4x squared plus 25. And I want to rewrite this in a way that's going to be useful for me using the trig substitution. So this is something that shows up inside an integral. I know I want to do a trig substitution. Well, what I notice is that this has the form of a squared x squared plus b squared. That means I want to go for the tangents. I want to use a tangent substitution. But in order to use that tangent substitution, rather than just memorizing things, the way that I would prefer to do this is to realize what I need is to write this. This needs to become a 1. So I will need to factor a 25 out of this and rewrite this as 25 times 4 over 25x squared plus 1. And then what I can do is I can say this is actually 25 times 2 over 5x squared plus 1. And then I can say, so this is going to be my tangent theta. This pen is really terrible. We're slowly getting rid of all of the pens that are terrible. Well, that didn't work so well. You can't see it, but I can bounce off the side of the garbage. So, you could memorize the table and then use that to figure out what substitution to do. But I don't personally recommend that. I personally recommend just recognizing the pattern. So you do have to memorize some stuff here. But rather than just trying to say, okay, so what is the substitution? I take this divided by this. Instead, remember, I'm just trying to get this into a format that looks like one of the identities. So it needs to involve a 1 and then something involving the variable squared. And that's the key. You figure out, what do I factor out here to get this to be a 1? And I can do that in other situations too. So for example, if I see something that involves, say, let's suppose that I have something like 1/6 minus 4x squared. And I know I want to do a trig substitution on this. Well, I recognize that what I want to get this into the form of is 1 minus sine squared theta. So this is going to need to become a 1. And that means I need to multiply everything here by 6. So this is going to become 1 minus 24x squared, and I factor out the 1/6. So now this should be my sine squared theta. That means that sine of theta should be equal to the square root of 24 times x. Now, what is the square root of 24? Well, 24 is actually 2 cubed times 3, so this is going to become 2 times the square root of 6 times x. And so that is my sine theta substitution. Now, notice that in this case, it actually picked up a radical. That's because we're not just dealing with perfect squares over here, but that's okay. It's just another constant to work with, and we don't have to really worry too much about that. It might make things a bit trickier in terms of the numbers involved, but it's not going to make things too bad. So again, I don't like to just think in terms of the pattern and then, oh, do I do A over B or whatever? I like to just look at the particular problem that I'm dealing with, and from the pattern, I then ask myself, okay, what do I factor? And that kind of automatically tells me what my substitution should be exactly in here. So, of course, this is going to work with the case where we recognize the secant pattern as well. If I have something like, let's say that I have 3x squared minus 4. Well, what I know is that I want to write this as secant squared theta minus 1, because I have a variable squared minus something. And I can rewrite this as 4 times 3 over 4x squared minus 1, and then this should be my secant squared theta. So that means that secant theta should be square root of 3 divided by 2 times x. And there we go. We've got this answer. And we've also got yet another terrible pen. So there we go. If you just memorize these patterns, if you remember the patterns, the nice thing is that each pattern is really just a form of the Pythagorean theorem. And so you're not really having to remember anything particularly new. You just have to remember the Pythagorean theorem formulas, and then you recognize which one of the forms of the Pythagorean identities do we have in this problem? What do I factor to get the constant to be a plus or minus 1? And then that tells you automatically what substitution to make, because whatever is involving the variable, that's going to be your trig function squared, and you can figure it out this way. So again, I'm not saying not to memorize the table. I'm just showing you, you don't need to memorize a table in order to do these problems. Now, the one other thing which we didn't really address here is, what about definite integrals with these kinds of trig substitutions? Well, when you do a definite integral with a trig substitution like this, these are just like doing indefinite integrals. The only difference is, well, there's two things. You could try just finding the antiderivative, convert everything back to x's, and then do the bounds that way. So if you get really confused, you can always do it that way. But you can also try to change the bounds. And the key thing is that if I have something like sine of theta is equal to a over b times x, or something like this, well, I just need to figure out what is the range of angle, what are the range of theta that will get me between my two variables. So for instance, if I'm going to be doing an integral that is from, let's say, negative 1/2 up to positive 1/2, and I have some f of x dx, if I end up making a substitution, like let's say sine theta is equal to x, well then my new bounds for theta, these are going to go from sine inverse of negative 1/2 to sine inverse of positive 1/2. So just like any other kind of change of variables, change of bounds kinds of problems, we do the same thing. We just convert from what would theta be when x is equal to negative 1/2 to what would theta be when x is equal to positive 1/2. And in this case, we know what the answers are. This is going to run from negative, let's see, sine is at pi over 6, so this is negative pi over 6 up to positive pi over 6. And we can do exactly the same kinds of things with the other trig functions as well. So the thing you got to remember there is just how do you do the inverse trig functions and things like that. And you do have to worry a little bit about the ranges there. So that is one thing that you're going to have to worry about when you do the definite bounds. In some ways, you might feel like you're better off just kind of going ahead and working out the antiderivative in terms of x's and then substituting things back in. Now, the one thing you do want to be careful about there is if you end up with an absolute value in your answers, then sometimes you have to worry about, well, are we actually doing the plus or the minus option on whatever's inside? Because that could potentially throw you in some of those cases. What I'm going to recommend you do, though, is just take a look at the examples that I've posted, because I think it's probably easier for you guys to read through those examples than to watch me trying to sketch it on these boards. And some of those examples show you how to deal with these definite integrals. And if there's any sort of situation that you find confusing, just let me know. But for the most part, it's really the same as any other variable substitution when you change the bounds. In fact, that's the thing that people tend to kind of miss when thinking about trigonometric substitutions. They are not some magical new kind of substitution. They really work the same as any other substitution. They just seem confusing because normally when we do a substitution where we substitute in a new variable for a function of x, or whatever our integration variable is. In this case, we are substituting in a function of theta for our integration variable. And yeah, that is a little bit different. Like, definitely that's not exactly the same as our other substitutions, but it's also not a totally new and different thing. Really, it's just changing one expression into another expression involving a new variable that makes the problem easier in both cases. I mean, you can even think of combinations, like maybe in some cases, I might want to do some weird substitution where I substitute a function of theta for a function of x or something like this. So that would be, another kind of thing. But fortunately for these types of problems, we don't have to worry about that. One more thing I want to mention with these kinds of substitutions, actually, this sort of brings us to what I just said, because it actually kind of does what I just said. What if I had an integral, but it didn't really explicitly look like one of the formats that we had? Like, let's suppose, just for the sake of example, that I had something like the integral of x dx divided by the square root of, what do we want to put down here? Let's suppose that I have x squared plus 3x. Actually, let's do 6x just because that'll be easier to illustrate what's going on. 6x plus 1. What are we going to do with this particular type of problem? Well, the key to one of these types of problems, actually, I'm going to do something else still. I'm sorry, I keep changing this around on you. Let's do plus 10, because that's going to make this work out a little bit simpler, and it'll really illustrate what's going on here. How do we do this? Well, we cannot just immediately do one of these trig substitutions, but here's what we can do. I can recognize that any quadratic expression in x can be rewritten as a perfect square together with some constant. So what I do is I complete the square on x squared plus 6x plus 10. This is actually equal to x squared plus 6x plus 9 plus 1, which is x plus 3 squared plus 1. So I can rewrite this original integral as x dx divided by the square root of x plus 3 squared plus 1. And now what I can do is I can kind of do this in 2 steps. Well, I can do it in 1 step or I can do it in 2 steps. It's kind of up to me. So what I can do is I can say, well, let's let u be equal to x plus 3. Then du is equal to dx, and x is equal to u minus 3. So this is going to become the integral of u minus 3 over the square root of u squared plus 1 du. And now this becomes a fairly straightforward trigonometry substitution, because now I can just say, well, I want tangent of theta to be equal to u. And now this is a standard problem like we've seen before. I mean, none of these problems are easy. It's still going to be a complicated integral, but it's turned into something like we have seen before. The other thing that I could have done is just right off the bat have said, well, forget about u's, although they kind of make it easier. What if I just set tangent of theta is equal to x plus 3? Then I can just do this substitution directly into here. So this is kind of what I was saying, where sometimes you actually want to set one function of one variable equal to some other function of another variable and see what you get. And of course, you can make this more complicated as well if you want to. So if you don't have something that's just like variable squared plus, in other words, if you don't have something that's like ax squared and b squared in your expression, you can make it that way by completing the square on whatever you're dealing with. As another example of this kind of thing, let's suppose that I'm dealing with an integral that involves, and I'm just going to do something similar here. Let's suppose I have x dx, and then in the bottom, I have the square root of, let's say, 4, let's say, minus x squared. Well, what I would like to do is I would like to rewrite this by completing the square on the denominator and then hoping that what I end up with in there is actually going to be something that I can do a trig substitution on. So how could I complete the square on this guy? Well, I can think of this as 2 minus 1/2 x. Actually, probably an easier way of thinking about this is we can rewrite 4 minus x squared. This can be rewritten as negative x squared plus x minus 4. And this is going to become negative x squared. Well, let's write it this way. X plus 1/2 squared minus 1/4 minus 4 from completing the square. And so what we end up with here then is going to be 1/4 plus 4, that's going to be 17 over 4 minus x plus 1/2 squared. So this is actually going to be equal to the integral of x dx over the square root of 17 over 4 minus x plus 1/2 squared. And then what I can do is I can do my substitution of sine theta is equal to x plus 1/2. Or I can go ahead and I can say, well, let's first set u equal to x plus 1/2, and then set sine theta equal to u, and do the u substitution this way. So by this clever use of completing the square, in both instances, I'm actually able to get this into a form where I can use trig substitutions. So like I said, I want to make sure that you guys spend some time looking at more examples, but I think the best thing is for you to read through those examples that I've posted rather than for me to just continue saying examples up here, because I think reading through them at your own pace is really the best way to understand these. They are not easy problems. They are very complicated. So make sure to ask me if you have any questions about these. I personally found these to be some of the most annoying problems in Calculus 2 when I was a student. And I still would say that these are pretty annoying problems. When I see one of these, it can take me a while to figure out how to do them. If somebody just throws an integral down at me and asks me to look at it, it can take me a minute to figure it out. So take your time with this, spend plenty of time on it, and just let me know if you have any questions. Like I said, I know this is a bit of a briefer lecture, but it's because I want to encourage you to spend more time this week watching the supplemental videos and reading the examples that I've posted as well. So I'm trying not to spend as much time lecturing as I might normally do. Anyway, I will talk to you guys again soon with our next topic.